Hey, welcome back, guys. Hope everyone's doing okay. Let me share the calendar. Today is the 11th. You have an activity due on the 13th, and then obviously next week we don't have any school, so we have a spring break. So now I will be gone this week, the following week, so I won't have much access to your emails. So I will get to them as soon as I get back. I'll be back that Saturday, the 20th. And then obviously on the 23rd, our next exam, chapter 7 through 9. What I plan to do is finish chapter 9. Let me go back to the page that we were at. I just got done with it in my 1 o'clock class. And we were on this channel. With this slide, we just finished this slide. We talked about the different pHs. Now, a thing about this is this chapter deals with the pH and the protons and acids and bases. An acid is denoted by a compound that produces a proton, which is a hydrogen minus its electron, hence a positive charge, and it has its own unique name, a proton. And then we talked about a base, where a base is anything that produces an OH or polyhydroxy ion called the hydroxide ion. Okay. We got into the pH, which is nothing more than a mathematical calculation. It's the log, is specifically the negative log of the concentration of the proton. Okay, a specific concentration that we call molarity, which has units of moles per liter. We will talk more about moles with time as time progresses. That's a very important concept also, moles. And so simply, you take the concentration of the proton and take the log, and you end up with a negative number, and then you multiply it by the negative in front of the log here, which you end up with a positive number. So your pH number, your pH values, which is the scale, should end up with positive numbers. So if you take 1 times 10 to the negative 5th, you can see the trend here. Nice even numbers, scientific notation of 1 times 10 to the negative 5th. You have a pH of 5, okay? 10 to the negative 8, pH of 8, et cetera, et cetera. Now you can put in scientific notation, or you can type it in longhand, 0.000, et cetera, 1, that's a pH of 8. So import it, put it in there as a decimal number, or realize that the exponent 1 times 10 to the whatever exponent, negative exponent, that number, that exponent is the pH of that value. You can also see, I hope, that as you decrease the concentration of the proton, as you decrease the acid concentration, the pH goes up and goes up into an alkaline range. The scale was from 0 to 14, with 7 being neutral. Anything less than 7 is considered acidic. Anything greater than 7 is considered basic. Okay, and then within the acid range, there's a strong acid and a weak acid, and the same with the base side. Some examples of different pHs of items that we're familiar with, variety of pHs, from a very low 2 to a very high, almost 12 for ammonia. Okay, so briefly, we're going to very briefly talk about what we call buffers, which is how they're related to the acidity. Buffers are nothing more than systems that are utilized to maintain a specific pH value. So we have buffer solutions that we can create from everywhere from 0 to 14 for whatever reason. If you need a buffer that has to maintain a pH of 3, we can create one very readily, where what that means is if an acid comes into the system, the base part of the buffer would react with it to maintain that pH we made it. Or if a base comes into the system, the acid part of the buffer would react with it to neutralize it to maintain that pH. Your blood, for example, has a very critical buffer system. And it's all related to sodium bicarb. It's related to carbon dioxide in your blood and in your lungs. It's all very sophisticated pH buffer system, but it's very crucial. You try to maintain a pH value somewhere 7.3, 7.4. Anything less, anything more causes, and that range is very small. Anything less or more can cause significant physical harm to you. Okay, so that's all a buffer does. It keeps the pH value constant, or whatever value you're striving to be at. We use that a lot in chemistry. We're doing reactions. We want to maintain a specific buffer range. We do that. We can set that up to create a buffer or whatever range we need. Now we have this chemical reaction. We talked before about chemical reactions. I got two reactants. Here's our reaction, our arrow, and that anything to the left of that yellow arrow there are the reactants, and everything to the right are the products. Now we talked about this also. This is a neutralization reaction. Now, how do I know that? How do I figure? Obviously, I mean, how do I know it from a Chem 130 perspective? Okay, I had mentioned before that in general, and this is not always the case, but in general, fairly large number of times, maybe 99% of the time, when you have a formula like this, okay, and you don't recognize that this is an acid we talked about before. This is nitric acid, but if you don't recall that, I stated that normally when you see hydrogen written first, as we got it right there, that's a fairly good indication that you're dealing with an acid, okay? Now, the other thing too, if you recognize the little trend here, the NO3 part, doesn't that look familiar with the nitrate, the NO3 -1, one of the polyatomic ions, okay? And so if you recognize the NO3 and you see there's a hydrogen up front, that's a very good indication that you have an acid. Otherwise, you can sit and memorize HNO3, that's an acid, it's specifically nitric acid. But the NO3 is a nitrate. In fact, all of those polyatomic anions were at one point an acid to begin with the H. As soon as you react that acid with the base, you form the salt, in this case, the nitrate. So the nitrate, when you put the hydrogen back in, you get rid of the ATE and you add IC acid, and you have nitric acid. Sulfate, same thing. Sulfate has a -2. You put two hydrogens back on, you got H2SO4. You change the name from sulfate to sulfuric. Get rid of the H, add IC and the word acid. You got sulfuric acid. Okay. So we see that we have a proton here. We recognize we got nitric acid. Okay. Then we come to the other species, calcium, in parentheses, hydroxide. So we got a hydroxide, which again should tell you I got a base here. Okay. Specifically, you're looking at terms right here. This is calcium hydroxide. Now, two things. I mentioned to you, if not, I'll refresh your memory. When a proton reacts with a hydroxide, you get water. Okay? Acid plus a base, hydroxide base, gives you water. You have neutralized the acid and the high base to give you water. Now, with that in mind, you can see that you have a hydroxide right here, obviously. More than that, you got two of them. And I need to neutralize those two acids. This is a neutralization reaction. So if I have two hydroxides, doesn't it stand to reason that I need two protons? And that is why I got a 2 in front of here, because each nitric acid has 1 proton. And I need 2 of them to neutralize the 2 hydroxides of the calcium hydroxide. Hence, I make, guess what? I make 2 waters, H2Os. Okay. Notice that coefficient in front. Now that coefficient in front of the formula, we can change any number of times, whatever value we need. Okay, we don't change the subscripts. The subscripts are etched in stone, but the coefficients we can change to whatever value we need to get things to balance. In effect, what we're doing here, we're balancing this equation, because one of the laws of physics and chemistry is the conservation of matter. What that means in essence is this: if I start off with 10 molecules of carbon in whatever form I have, it could be any form, and I do something chemically to those carbons, I will end up with 10 molecules of carbon at the other end, but they would be in a different form. Okay, a lot of the carbon we ingest eventually gets converted to carbon dioxide as we exhale to our metabolic system. So that carbon that may have been on a fruit or may have been part of the meat, we ingest that, it gets incorporated into our system, we metabolize it, eventually we excrete it. This time it's carbon dioxide as gas, so it's still carbon with 6 carbons, whether it is in fruit or whether it's in carbon dioxide, it's still carbon. And that's what we're doing here. We have 2 protons in the form of an acid. They react with 2 hydroxides and they create now 2 waters. So altogether, I had 4 hydrogens. Okay, I have 4 hydrogens, 2 of them in the hydroxide, 2 of them in the acid. Now I got 4 hydrogens in the form of water. Okay, with that 2 times water, each has 2 hydrogens. So we have balanced this reaction. This is very important that we're going to learn to be doing balancing chemical reactions. It's understood that there's a 1 in front of this. When there's no number in front of the species, like in math, it's understood to be 1. Well, why do we need to do this? Because eventually we're going to do things like this. We're going to say, all right, for some reason, I need to make 1,000 grams of water. Okay. Question is, how many grams of calcium hydroxide do I need to start off with? These are type of typical equations we can have. We're going to be using. What we're going to do is, what we've learned is, first of all, we need to figure out the molecular weight of each one. Because we need to figure out there's 2 hydrogens, 2 oxygens, 1 calcium. We can add up the atomic weights for each one. We got a molecular weight. We're going to eventually use that information to do some calculation. Now, I went from product to reactant, but I could easily go the other direction. If I have 10 grams of nitric acid, how many grams of water will I generate? And I can only answer that question after I balance this chemical equation. And that's what those numbers up front do. Okay. Anyway, a lot more on that later on. That's an introduction to you of what's coming up. So the question is, blank is the Arrhenius acid. Well, in this case, it would be nitric acid, because by definition, Arrhenius definition is any species that produces a proton, not a hydrogen, totally different. So your answer by saying hydrogen would be incorrect. Your answer by saying either H plus or proton would be correct, okay? And the base is any species that, for Arrhenius base, any compound that will produce hydroxide, and calcium hydroxide does just that. Okay. Now, why does calcium produce 2 nitrates? Or what do we know about calcium? Calcium is an ion. Hold on. My thing's going crazy here. Calcium is an ion. +2 is a +2 ion. the nitrates from your polyatomic table is a -1. So you can see I need 2 nitrates to balance out the +2 charge of calcium ion. And that is why you use 2 calcium nitrates. Now, if you go through this, you will see that that equation is balanced. For example, who can tell me how many nitrogens total are in the reactant side? If we look at this reaction up and down. How many total nitrogens do we have on the reactant side? That's over here on this side. How many total nitrogens do we have? Do we not have 2 nitrogens total? Three? No, not 3. Only 2. Okay. Only 2. You see that 2 in here? That 2 represents 2 molecules of nitric acid. Each molecule has 1 nitrogen, so I have a total of 2 nitrogens. When I come over to the right side, I have 2 nitrate polyatomic ions. Okay, because my subscript is 2. So on this side, I got 2 nitrogens. So nitrogen, you have fulfilled one of the laws of chemistry, conservation of matter. I got 2 nitrogens as in the form of nitric acid on the left and 2 nitrogens on the right in the form of nitrate. And you can go through the whole process and you can see I got 1 calcium here, 1 calcium here, that's balanced. I have 2 hydrogens here and 2 hydrogens here, a total of 4 hydrogens. I have 4 hydrogens in the form of water because I got 2 molecules of water. Then I got 6. Who can tell me how many oxygens do I have in the reactant side? How many oxygens total do we have on the reactant side?
2.
All together, try again.
6.
4.
Oh,
Yep.
actually, wait. 8.
How many? Try again. Oh, I heard 8. Okay. That is correct. The answer is 8. Okay. Okay, let's find out. Let me clear it so it won't be so messy here. Okay, we have 8 oxygens. Question is how? Well, I got 6 here total from the nitric acid, right? Because each nitric acid has 3 oxygens, and we have 2 of the molecules of those. So it's 2 times 3 is 6. And then the hydroxide, I have 2 hydroxides. Okay, so there's 2 oxygens coming from there. So I got a total of 8 oxygens. Okay, over here, I got 2 in water, 2 oxygens here. And on the right side, see the nitrate has 3 for every nitrate inside the parentheses, and there are 2 nitrates. So 3 times 2 is 6. So I have 6, so a total of 8 oxygens on both sides. Okay, and then I got 8 right here, 8 right here. So oxygen, you have balanced Mother Nature. Okay, you got 8 in the left, 8 in the right. Okay, now here, and that's what I'm saying is that there's still oxygen. They still have 8 protons, whether in the form of hydroxide or whether in the form of the nitric acid or the nitrate. It's still oxygen. And we have balanced nature. Okay, let's move on. All right, so here's asking you a question. They want you to draw pictures of these chemicals here. Now, recall that we had diagrams that describe strong acid, strong base, weak acid, weak base, weak base, strong base. Okay. Well, if you're given this information, this question, the first thing is this systematic approach. Okay. First of all, we're dealing with ions here. Some of these ions are going to be 100% dissociated, some are not. But the first step for me, if I'm working this problem, is I would break it down first with the ions that I'm going to create. And so if I look at HNO3, the ions that were going to be created will be H plus and NO3 minus. Okay, so I'm looking at that first. I'm going to get all the ions worked out. Next one, HF, same scenario, similar. I'm going to make H plus the proton and the fluoride ion. Okay, then KOH. Well, I see I got potassium, so I'm going to make the potassium ion, and the OH is the hydroxide ion. So what I'm doing right now is writing down all the ions I'm going to make, because I'm going to have to draw a picture of a diagram to represent them in the solution of water. So let me get the ions. So we got magnesium. We know that magnesium is a +2 ion. It's in group 2, becomes a +2. And we have hydroxide here in parentheses, which should flag to you, I have a polyatomic ion, specifically the hydroxide. Okay, and I don't leave the fact that there's 2 of them because of this in the parentheses. Okay, so first thing I did was write down the ions. Now I'm going, if you recognize already what they are, then by all means go to the next step, but I'm going with the pretense that you don't recognize everything at this point with respect to the ions. So I'm breaking them down because I need to draw these eventually. Now the next step, we've been talking about strong acids, weak acids. I've been talking about strong bases, weak bases. Now what we meant about strong was the fact that they either completely dissociated or maybe only about 5 or 6% have dissociated. Dissociating means that they break apart, okay? HNO4, we had defined earlier as a strong acid, okay? Which tells you that we're going to dissociate this thing roughly approximately 100%. Okay, so that means that the ions that we make are going to be totally all just ions. HF, we had defined earlier as a weak acid. It is a weak acid compared to HCl and so forth. It's a weak acid because that bond is very strong and it holds on to that hydrogen very strongly compared to hydrochloric acid, HCl, which that bond's a little bit weaker and it doesn't hold on to the hydrogen proton as well. So it's a strong acid for HCl. Okay, KOH, we define that as a strong, so anyway, weak acid, I don't know, less than 5% dissociation. Remember we said weak acids 1 to 5. KOH, now right now, we defined it and told you that it is defined as a strong base, but you're going to learn from the solubility rules that anytime you see potassium, it's going to be soluble in water. And when it's soluble in water, strong electrolyte, in this case, strong base, but we'll get to that here in a second. But we just told you potassium hydroxide, strong base. So that implies, you know, approximately 100% dissociation. Okay. Then magnesium hydroxide, we told you that it was a weak base. This too, you will find out based on the solubility table, why this is a weak base. It is a weak base because it is classified as insoluble in water. Doesn't mean that it doesn't, that any doesn't dissociate, means that, okay, that the bulk of this material stays together and only a small percentage of it dissociates, and hence it is classified a weak base. So step number 2, first step was to define the ions I'm working with. Second one to define whether it's strong or weak, because that would tell me if I'm going to have to draw them kept together or separated as ions. Okay, once I know all that information, I can proceed now with drawing the diagrams. So we got this scenario. Now here's the solubility rules. I'm introducing them now because we're going to talk about this here in a bit, but these are the rules that define when it comes to inorganic compounds, whether a compound is soluble in water or not, insoluble. When we say the term soluble, we say that it will go completely 100% dissociated. When we say insoluble, that means that the bulk of it, maybe 99% of it, remains intact, but there always will be some of it in ionic form, in ions, okay? All right, HNO3, nitric acid. We defined it to have be a strong acid, okay? And we also went and determined the ion. So what I'm going to draw be something like this, where the ions are all separated. Now I put 3 sets of ions. Don't forget to put the charges on them because they have totally dissociated, okay? I just put 3 sets. That's all you need, 3 or 4 pairs. Don't just put one, just put the protons and forget the counter anions. Because again, in nature, you got always have the charges come in pairs, okay? So totally dissociated represents a strong acid, okay? A lot of ions in solution. HF, we defined as a weak acid, okay? Which means that the bulk of the material of the compound is still intact. They are written together. They are maintained together with no charge. But we have to show at least one pair of ions. And hence we're showing H proton and the fluoride. Because even though it is classified, it is a weak acid, there's a little bit of ions in solution, okay? Then we have potassium hydroxide. That has been defined as a strong base. Now, the reason it's defined as strong base is if you look at the periodic table down here, number 1, we're going to bring this up here in a bit, but any anion that's bonded to those 4, lithium, sodium, potassium, and ammonium, I call them the big 4 there, the big 4 cations, they are 100% soluble. When they are 100%, they're soluble, they are very strong electrolytes. We're going to learn about that word electrolytes. So they're totally dissociated, which in this case, totally dissociated means they're being a strong base because it produces the hydroxide. As is the case with nitric acid, I put 3 partners in there. You could put 3 pair. You can put 4, whatever number you want to put in. 3 to 4 is sufficient, but make sure you put the ions, the charge to each ion. And at least, again, make sure you have enough of each to be paired up. Now, it is okay to do this. I don't have a problem with this, of writing it and say, okay, I got 3 potassium ions and 3 hydroxide ions. That's perfectly okay with me. Same thing. You don't have to draw them all out. The same thing over here. I could say, I don't know, on the other side, I could say, I got 100 protons and 100 nitrates. Okay, that's fine with me. You can do it that way, or you can individually write 300 protons, 100 protons. You don't need to add that many. But. All right, the next one, magnesium hydroxide. We told you it is a weak base, but now I'm going to tell you why. If you look at the solubility table, this table is broken up into 2 columns. Let me erase this real quick. The first column in yellow is the soluble column, okay? And the second column on the right-hand side is the insoluble column. I'll get more detail here about that in a second. But if you look at the hydroxide, which is number 10 in this table, it's in the insoluble column. Unless the hydroxide is bonded with number 1 on the soluble side, then, or any of the others that are soluble, calcium, strontium, and barium. So there are only 7 compounds that are soluble in water. Everything else is insoluble. Magnesium is not part of the big 4, and it's not calcium, and it's not strontium, and it's not barium. So that means it is insoluble, which the way we draw that would be as follows. The bottom chunk material represents the magnesium hydroxide. Because it is insoluble, the bulk of it is still in solid form and drops to the bottom of the container. We have to show at least 1 pair of ions in solution. And hence we got Mg2 and 2 hydroxide. We have 2 hydroxides. Why? Because in parentheses, we show 2 hydroxides. We need 2 hydroxides for every magnesium, okay? This is, if you have any milk of magnesia at home, that's magnesium hydroxide. You would notice if you take some milk of magnesia and put it into a clear glass, that it will separate. Let it sit there for a while. It will separate. What's forming the white powdery material on the bottom is the magnesium hydroxide. And then you'll have some in solution. Okay. So here we represented 4 different compounds, chemicals, and showed them to be how they would be represented if we dissolved them in water. And we base that based on whether they are strong acids or strong bases, weak acids, weak bases, or whether they're soluble or insoluble in water. Okay. Okay. So let me summarize here real quick. Somebody has a question. The question is, will we draw all the insoluble compounds with metals as a solid at the bottom? That, yeah, just like that, but metals without charges. If you notice, let me back it up. This down here at the bottom of magnesium hydroxide, it just represents, magnesium hydroxide that would settle into the bottom. It'd be a precipitate, okay? And if this was a solid metal like copper, obviously it would drop down. They won't dissolve at all. Okay, I hope that answers the question. Yeah. All right. So summarize. With respect to Arrhenius definitions, anything that produces a proton in water is classified as an acid, an Arrhenius acid. Okay. If it produces a hydroxide, polyatomic ion in water, it is classified as an Arrhenius base. Now, Bronsted-Lowry and Arrhenius acid, the definition of Arrhenius and Bronsted-Lowry for acids are the same thing. Whether you make a proton or you lose a proton, you're creating a proton. So, tomato, tomato, they both share the same definition from my perspective. Where they differ is the base. A chemical that takes on that proton that an acid produced is, by Bronsted-Lowry's definition, a base. And normally, a lot of times, we're looking at chemicals that are, let me draw something real quick. You can see that the hydroxide polyatomic ion has 3 pair of lone pair electrons, right? Has a negative charge. The proton has that empty orbital, plus charge. So you can see where the proton, the hydroxide accepts that proton to make a bond, right? In this case, it makes water, H2O. But then we have species, and that's the hydroxide. So even hydroxide under the Bronsted-Lowry definition fits. But for those compounds that do not deal with hydroxide, they will deal with lone pair on the central atom. Remember the Lewis dot structures for ammonia. You will find that compounds that have lone pair are good candidates to be in Brownstein-Lowry bases because, as the case with the hydroxide, the proton coming up here can hook up and create the ammonium ion, which we also did the Lewis dot structure, but now it has a plus charge. Okay. So with respect to Brownstein-Lowry bases, it has nothing to do with hydroxide at all. Okay, it just expand the definition of bases and encompass more compounds that can act as bases. Strong acids ionize 100%, ionize, dissociate, same, dissociation is the process of separating to form ions. Okay, so they become ionized 100% or approximately 100%. Weak acids ionize much less. Strong bases dissociate 100% like the acids, and obviously the weak bases dissociate much less. Okay. And buffers, their sole function is to maintain a pH value, whatever that pH value may be. Some more examples of your favorite soft drink and the pH values. You got tap water up there, slightly acidic. That tap water varies from your water source. You like to think it's around 7, but like I may have mentioned this, but in Kansas City, in the area, I used to have my students come in, we analyzed the water from all around the metro area, and we had values from as low as 6 and as high as 10 and 7, a little bit above 7, but quite diverse. Okay, why are you concerned about this? Well, this can happen. You don't want that to happen to your enamels, because your enamel gets broken up quite easily. Okay, this brings us to solubility. Any questions before I progress? All right. When we talk about solubility, we're talking about an amount of solute. That's the amount of material that we can dissolve in a given amount of salt. Okay. So, and also we deal with a temperature because solubility is a function of temperature. Obviously, as you may or may not know, if something doesn't dissolve, what do? You heat it up and it goes into solution. So we're specific at 25 degrees temperature, and it's a specific amount of solvent. You know that if I take a gallon of water and a teaspoon of salt, it's going to dissolve, right? Boom, I got a little bit of salt water in there. But if I take 10 pounds of salt and a gallon of water, I may have a little bit of a problem dissolving that salt, even though sodium chloride is soluble in water. So yeah, that's what they mean by a given amount of solvent. Now, when something is classified as soluble, we're saying that it's totally 100% dissolved, associated, and its physical state now is given by the parentheses AQ, meaning an aqueous solution. We aren't talking about water, an aqueous solution. When something is classified as insoluble, it says that the bulk of the material does not go into solution no matter what we do, unless we up the temperature, but we're not going to do that. But the bulk stays out of solution, but there is a small amount that does go into solution. Okay, very small percentage dissolves. Since the bulk of it is insoluble, we use the physical state as S, parentheses S, to designate solid. Now, as I mentioned before, the solubility rules, which are found on the periodic table, bottom right corner, are broken up in 2 columns. Okay, so let me make sure I got the right one here. First column is here designated as the soluble column. Okay. Number 1, Okay, these guys are called call them the big four. All right, the big four, because when any compound is partnered up with any of these cations right here, lithium, sodium, potassium, and ammonium, 100% all the time soluble. So no matter what the anion is, if it's lithium, potassium, sodium, or ammonium as the cation, soluble. No questions asked. Okay. Number two, that's the acetate ion. That's the other polyatomic ion. That comes from acetic acid. Acetic acid is an acid. When you react a base, when you react a base with it, it forms the anion, which is the acetate. Try this at home. You could take baking soda and vinegar, you put them together. The base is baking soda, sodium bicarbonate. The acid is acetic acid. Okay, they will react. It's going to bubble up, which is carbon dioxide. And one of the products you make is, guess what? Sodium acetate. Okay. So when the anion sodium acetate is bonded or connected to any cation, doesn't make a difference what it is soluble. Copper acetate, iron acetate, chrome acetate, so the list goes on. Any of the metals, soluble. The same is true for number 3, the nitrate ions. Any cation bonded to the nitrate ion, regardless of the metal, cation, it is soluble. Okay, so far so good. Number 3, a little bit of a curve. All the halides, not all the halides, the halides, chloride, bromide, and iodide, when they are bonded to any metal, they are soluble, except when they are bonded to silver, mercury, and lead. Okay, see how that works? So of all the compounds in the world, so to speak, there's only 3 halides that are insoluble in water. And that is silver halide. The X represents either the chloride, the bromide, and iodide. The silver halide, the mercury halide, and the lead halide. Okay. In fact, that's how one way we test for chlorides in your water. We hit it with a little bit of silver nitrate solution. And if you got chlorides or bromides or iodides, it will form a precipitate. Okay. And even the color of that precipitate would tell you if it's a chloride, a bromide, or iodide. All right. Number 5, sulfate, SO4 -2. Totally soluble with whatever metal you bind it with, except calcium, strontium, barium, silver, and lead. Those 1, 2, 3, 4, 5 examples are insoluble. Every other sulfate is soluble, okay? Which tells you 100%. So if you need to write a diagram of any other one, they'd be all separated, okay? So you see how that works for the soluble side. The insoluble side, a little bit more interesting, I think. Number 1, or it could be number 6, depending on the table. The chromate, CrO3 -2. No matter who they are bonded with, the cation, they are insoluble except with the big 4. Okay, you see how that works? So if I have lithium carbonate, sodium carbonate, potassium carbonate, or ammonium carbonate, those guys are soluble. If that carbonate hooks up with any other partner, it is insoluble. Same is true with chromate. Chromate, everything's insoluble except with the big 4. Phosphate, same thing. Everything is insoluble except with the big 4. And the sulfides not only have the big 4, but there are 3 more. So there are 7 examples. Oh, wrong. Where's my the calcium sulfide, strontium sulfide, barium sulfide, plus the 4, there's 7 examples of sulfides that are soluble, which means that everything else is insoluble. And then the hydroxides are insoluble except calcium, strontium, barium, and the big 4, guess what? Okay, so again, you have 7 example soluble hydroxides, and the rest of the compounds in the world are insoluble. Okay, so with that in mind, let's look at the answers here, the questions. They're asking you here, using the solubility rules up here, is it soluble? And then to give the physical state. Well, tell you what, number one, you didn't even have to think about, right? Because, yeah, no problem. Yeah, if your internet backs up, don't feel free to come back in. Feel free. All right. The fact that you see sodium up front, that's all you got. It's all she wrote. That's the part of the big 4. It is soluble. You don't have to go any further. Okay. So it's aqueous. That's how we write it. It's an aqueous. So if I take sodium sulfide, put it in water, it will dissolve 100%. And if I would draw a diagram of these guys, I would have to draw them with the ions all separated. Okay, magnesium hydroxide. Well, I look for the hydroxide, which is number 5 on the soluble side, insoluble side. Okay. Aluminum is not part of the big 4, nor is it part of, it's not calcium, strontium, or barium, which will make them soluble. So that means that this guy is insoluble. Aluminum hydroxide is insoluble. Okay. Silver bromide. You would think the bromide, will be soluble because it's in the soluble side. But remember, there are 3 examples where they are insoluble. And one of them is silver bromide. So silver bromide is insoluble, therefore it's soluble. Okay. Calcium carbonate. Well, we go to the carbonate, which is on the insoluble side, number 1. Okay. Calcium is not part of the big 4, and that's the only soluble carbonates that are there. So this guy would be insoluble. You may have seen this. Yeah, you may have faucets where you got a white powder material around your spigot, or you may have ring around the tub. That is calcium carbonate. The calcium, there's a lot of calcium and a lot of carbonate in our waters. They're not very soluble, and over a period of time, they will build up, and you get this white material, crusty material on your faucets. Finally, the last one, potassium. The fact that it is part of number 1 in the soluble side, the big 4, you don't have to go any further. It is soluble. Okay, so aqueous. So if I were to have to draw these things in a beaker, okay, the fact that this is soluble, okay, I had a little beaker, I would draw my little sodium, couple of sodium and my sulfide in solution, totally separated. Aluminum hydroxide, I would have a little chunk of aluminum hydroxide down at the bottom, and then I would have my aluminum ion and my 3 hydroxides in solution. Okay. My silver bromide, which is insoluble, if I need to draw this in water, at the bottom, it'd be a big chunk of silver bromide down here together intact. But then I would draw at least 1 set of ions in solution. Okay. Same is true with calcium carbonate, because it is insoluble. Big chunk of it be down at the bottom. I would have my calcium plus 2 ion and my carbonate ion in solution with the respective charges. And down here in the bottom would be calcium carbonate intact. And then the last one, because everything is soluble, we got potassium in solution and nitrate in solution. 1, so I can add maybe 3 of each, and that'd be good. Okay. That's that is how I would depict a beaker of those choices if I had to write a beaker full of those. Why would you write solid? Okay, because if it's insoluble, it's a precipitate. Okay, so anything that is insoluble, let me restate that. Anything that is insoluble, calcium carbonate is insoluble. We will write the notation S. But also keep it in mind that there is still a little bit of it in solution. And so as right here, soluble. An ionic compound that does not completely dissolve is classified as insoluble. Only a small percentage of it dissolves. Nevertheless, because it is insoluble, it is a solid in a water solution. Okay, does that make sense? So that's the case for silver bromide. That's the case for aluminum hydroxide. Okay. All right. Let me see. So electrolytes. So when these materials, these compounds, these go into solution, they form these charges, these ions. These ions are electrolytes. We're familiar with them. You purchase them when you go get yourself a drink, right? Electrolyte drinks. All you're buying is metals with charged metals, which either lost or gain electrons. But those electrolytes are important, at least in our body, for a lot of things, because without those electrolytes, we could not send signals in our body, okay? Because those electrolytes carry the charge. So something that's a strong electrolyte, they are good conductors of electricity because their chemicals have been ionized in water. So things like soluble ionic compounds that designate are soluble based on the solubility rules are strong electrolytes. Strong acids and strong bases because they completely dissociate 100%, okay? Things like potassium bromide, nitric acid, potassium hydroxide, sodium chloride. Okay, those are all strong electrolytes. Non-electrolytes. Now, these are covalent compounds. Remember, acids like nitric acid, hydrochloric acid are covalent compounds. Normally, covalent compounds, when you put them in water, do not dissociate. The only exception to that are acids. They dissociate to produce a proton. That means that all the other electrolytes that are not, all the other covalent compounds that are not acids do not dissociate. They don't produce ions. So water, 100% water, pure water is not a conductor of electricity. That's why if you fill up a tub with DI water, deionized, that means all the ions have been removed, and you throw in your electric dryer that's been plugged in, there's not going to be any current passage. You're not going to get electrocuted. We won't do this at home because eventually electrolytes get in there. Your tub hasn't been cleaned up very well. Electrolytes can get in there. And once you do that, now you form a conducting solution. Sugar, this is the general structure for sugar: 6 carbon, 12 hydrogens, and 6 oxygens. Now, even if you didn't know that was sugar, the fact that you see nothing but carbon, hydrogen, and oxygen, and the fact that there's no hydrogen up front of the molecule to designate an acid, would tell you without the hydrogen up front, they're more likely you just have a covalent compound made up of nothing but nonmetals, carbon, hydrogen, and oxygen. They are non-conductors. They will not conduct electricity. Okay. The weak electrolytes are poor conductors of electricity. And they only partially dissolve. They're partially ionized. So things like the weak acid, the weak base, any of the insoluble compounds, okay, they don't have ions. They only have a little bit of ions in solution. So things like hydrofluoric acid, magnesium hydroxide, which is a weak base, and we know it's weak because magnesium hydroxide is insoluble in water. Silver chloride is weak because it's insoluble in water, and carbonic acid is a weak acid, okay? And a weak acid. So those guys will be weak electrolytes. The overview here, strong electrolytes are the strong acids, strong bases, and any ionic compound that's soluble. The weak one, the weak electrolyte is a weak acid, a weak base, and any of the insoluble ionic compounds. And then the non-electrolytes are the covalent compounds. They will not cause charge. It's like this. Those little, the red and the blue balls there, they represent charges. They represent the ions. And you have current passing through these through electrodes, okay? Now, if you have a strong electrolyte, you're going to have a lot of current. If this was a light bulb up here, it will light up. A strong electrolyte would give you a bright light in that light bulb. A weak electrolyte, though, will give you a light up the bulb. It will be lighted. It will light it up dimly, okay? Because there's not that many ions in solution, but there's enough to pass the current. And non-electrolytes, it's like a light switch. The ions act as a light switch. When you have ions, the light switch is on, you're closing the circuit. You complete the circuit, electricity passes by. When you have non-electrolytes, no current is passed. Okay, so no electricity is conducted. So you get no charge here. All right, so here we have 3 images. Some of these we talked about already. They ask you which is strong, which is weak, which is not. I think you can see already the first one, okay? You have a big chunk of magnesium hydroxide at the bottom. That should tell you that you have a weak electrolyte because we only have one pair of ions in solution compared to way over in the far right where you got potassium chloride, where you have all nothing in, it's a solid, everything's in solution. Furthermore, you know that potassium belongs to the big 4 based on the solubility rules. So there's 100% dissociation. Then the one in the middle, it's all made up of nothing but carbon and hydrogen. So there's no charge there. So that would be a non-electrolyte. Okay. The weak would be the first one, and the strong one would be the far right, potassium chloride, as far as electrolytes. All right, which brings us to this list here. And I'm just going to give you the scenario. We'll talk about it. Number 1, we have barium sulfide. Okay. Now, this is where we put it all together a little bit, because you could be asked a question, give the name, say, write the name, write the formula for barium sulfide. So you got to go find out the ions for barium and sulfide. And now it's going to ask you, is it a covalent or ionic compound? Then it'll say, okay, is it soluble in water or not? Okay, see how it progresses? When you're starting off with just the ions and then build up on it. Okay, so barium sulfide, we know that it is a strong electrolyte. We know that because if you look at the solubility rules, sulfides, okay, barium sulfide specifically, are soluble. Okay, any other sulfide that's not part of the ones they listed there and the big 4 are insoluble. And so this is why barium sulfide is a strong electrolyte. So in that little sensor with the 2 electrodes and the light bulb, that light bulb will be bright. And we have a current running through there. There'll be a bright light on it. Silver chloride. It's a weak electrolyte because solubility rules tells us that it is insoluble. So going back to the example of the light bulb will light up, but it'll be dim, okay? Because they have a small amount of ions in solution. Potassium. Well, the fact that potassium is first should tell you right away it's part of the big 4. So it's soluble, therefore strong. Electrolyte in the light bulb would be bright again. H2CO3. The fact that hydrogen's written first and it's not H2O but the fact that it's something else, CO3, and you recognize CO3 as a carbonate, that tells you I got an acid here. And furthermore, is one of the acids that we said is a weak acid. Okay. Therefore, it's a weak electrolyte. CO2 is covalent. No charges involved here. Covalent compounds don't produce ions, so it is non-electrolyte. Number 6, sodium hydroxide. Without thinking about it, sodium's written first. Automatically, it's soluble because it's part of the big four. Okay, and it's a strong base. Okay, so very strong electrolyte. Calcium carbonate, otherwise known as ring around the tub. Okay, precipitate. It's insoluble in water. Therefore, it is a weak electrolyte. And then we got this generic C6H12O6. Okay, hydrogen's not up front, so not an acid. Therefore, it's a covalent compound. And so you can say made up of nothing but carbon, hydrogen, and oxygen. And so it's a non-conductor, non-electrolyte. That is the structure for one of the sugars. Well, almost done. Number 9, we got sodium first. Okay, right off the bat, it is part of the big four. It's soluble, therefore it's a strong electrolyte. And then lead sulfate. Moment you see lead, that's a flag for possibly a precipitate. Depends on what the partner is. In this case, it's a sulfate. You look up sulfates, you'll find it in the soluble column. However, when it's bonded to the big metals, it is insoluble. Therefore, it is a weak electrolyte because it is insoluble. Okay. All right. Any questions? Other than that, congratulations. One more chapter down. Chapter 9 down. We will continue with chapter 10 when we get back. So I'm not going to start another chapter for 15 minutes. So, any questions or comments?